we'll go ahead and get started. So I started off this presentation here with a quick rundown of some related vocabulary. I think sometimes when we teach biogeochemical cycles, we we forget there's a plethora of vocabulary terms that relate to biogeochemical cycles, and as students, you have to be able to connect cross content here because the exam is accumulative, right? So it's over everything. So you may get a free response question that talks about hydrology or the hydrologic cycle, and that's really in really fancy terms, that is it's the water cycle, right? So I put down a list of just terms that often are associated with biogeochemical cycles that students just maybe forget or they don't think about. And hopefully by the end of this, we will, have a better concept of, what's going on here. Okay. But we'll go over the vocab real quick. I mean, obviously, biogeochemicals, whether it be carbon, hydrogen, oxygen, whatever it might be, those are resources. Because they are in the cycle form, we would probably lean that most of them are probably renewable. And then when we get into like maybe population dynamics, and as a population continues to grow, maybe some of these resources become limiting factors and they kind of teeter on the phase of non-renewable. But they are renewable. And then the limiting factor component here as density dependent limiting factors or density independent limiting factors. Again, that kind of goes back to sheer number. If you have more of a certain organism, then you might be looking at density dependent limiting factor. That means as the population continues to grow, the resource becomes more of a factor, right? And limiting factors, we go back and remember that limiting factors are something that can limit the size of a population. So, and also, as you guys are listening, when I say population, my students, I know for sure they kind of lean back to like human population. Oh, well, he's talking about people again. He's talking about human beings, and that's not always true. And that is probably one of the toughest things to decipher in AP Environmental Science is, are we talking about people population? Are we talking about organisms, animals, plants? What kind of population are we talking about? So keep that in your mind. These are all abiotic, so they're all non-living factors, right? Macromolecules are something we'll talk about. Carbon sinks, eutrophication, that's a big one. Sometimes that's referred to as cultural eutrophication. Biogeochemical cycles tie in with the greenhouse effect. Of course, that leads us down the dark rabbit hole of global warming. And what is global warming? And is it the same thing as the greenhouse effect? And then we get into some ocean acidification, ecosystem services. We'll touch a little bit on legislation. And then, of course, man-generated, anthropogenic, or synthetic. And then feedback mechanisms, positive and negative feedback mechanisms. All right. We'll keep going here. All right, if you had to break down your biogeochemical cycles, you can break them down right here like this. Schnapps, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. And maybe a little mnemonic thing there where you can hopefully memorize that going into your AP exam. The idea here for these presentations, these Saturday sessions, is to try and give you a little bit of a deeper understanding, but also to kind of give you, a refresher course. Some of this hopefully is review for you. And by reviewing it, you'll set it to some long-term memory storage there. And of course, if you guys, at this point, if you guys have a question, you can put it in the chat, or you can unmute yourself and ask a question. I have no problem with that. Are these elements biotic or abiotic components of the ecosystem? You know, how can these be arranged into 5 major biogeochemical cycles? These are some things that are coming up on this next slide. And so we break down our biogeochemical elements into these 5 cycles. This is H2O, the water cycle, the carbon cycle, nitrogen cycle, phosphorus, and then sulfur. Unfortunately, we're not going to spend a lot of time talking about sulfur. It doesn't make up a large aspect of the living organism. And so we're not going to talk about that cycle very much. If I'm looking at AP Environmental Science and I'm trying to get prepared for the exam, and sulfur is something I want to research or look into, I'm probably going to put most of my time into carbon, as in coal and burning coal and releasing sulfur and sulfuric acid and that kind of stuff. So that's probably, if you were going to say crunch time and study for the AP exam, you're going to lean most of your efforts into sulfur as it's related to the non-renewable resource of coal. All right, we take a look at the organism here, and it breaks down the percentages. You know, 65% oxygen, carbon, 19%, 10% hydrogen, and then we got nitrogen, and then phosphorus is at 1%. Okay. So we can see the H2O there makes up quite a bit. We are living organisms, so we do contain the element of carbon there, or this ratio of carbon, hydrogen, and nitrogen, or carbon, hydrogen, and oxygen, sorry. And so that makes us organic. All right. Let's keep moving here. The water cycle. So right now, if you would, in that chat, why don't you go and put down, if you can write down as many words, maybe 3 words that go with the water cycle. Put that in your chat real quick. So go over to the chat and type up some terms that come to mind with the water cycle. I see someone put precipitation, evaporation, condensation, good. Transpiration. Transpiration's always one of those that students sometimes forget. Okay. Good. I see the chat room filling up there. Infiltration. Ooh, someone's trying to get bonus points there. Because a lot of students don't really even think of, they think of runoff, right? You know, we think runoff. All right. So you guys are going to do really, really well with, I see groundwater. You guys are going to do really well with the water cycle. Most of my students come into class, they already know all of the condensations and the evaporations and all that stuff. The movement of water is dependent upon the physical changes which allow it to be either a solid, liquid, or gas. So I think for the deeper meeting here, you need to definitely be able to connect the water cycle to the phase changes of water, you know, whether it's a solid, liquid, or a gas. You hopefully understand that, you know, liquid water, as it gains energy, it jumps up to that gas state. And as it loses energy, it reduces down into that liquid state. And if it loses more energy, it'll reduce down to that solid state. Okay. And so energy is a huge component here to the hydrologic cycle. It's definitely a big factor. And so if I'm connecting this to other topics, this is something that's going to play into weather and climate, right? You know, as we're near the equator, you're getting more direct sunlight, right, at the equator. And so those rates of evaporation tend to be a lot higher in those areas, right? And then as you move, you know, north or south, away from the equator, you know, you get more glancing rays of sunlight. And so the rate of evaporation is going to change dramatically. Other factors that play into the water cycle would be how, you know, the northern hemisphere definitely has a little more land mass than the southern hemisphere. And so whether that land absorbs heat, right, or reflects heat, so we're talking about albedo, the reflectivity of an object. And so there's a connection to those things and the hydrologic cycle. And so I think if you have a really deep understanding of the water cycle, you're going to have a better understanding of how to address questions when we're talking about, say, the water cycle of the Colorado Rockies, right? It was a few years ago when the free response question talked about climate change, the water cycle, and the Colorado River. And so a lot of students, well, one, my students didn't realize that, you know, it was the ice pack melting. You saw the snow-capped mountains melting, and that's what provided water to the Colorado River, right? And so what ended up happening is the students didn't understand that to start with, and then they had to tie in climate change. Okay, so in the chat, real quick, how could climate change? Just try to jot down what are some ways in which climate could change that may impact the water cycle. All right, nobody's writing anything in the chat. Where are you at? There we go. Okay, so first off, let's talk about change, right? So automatically in change for climate, okay, there's two big factors that play into climate, right? That would be annual precipitation and annual temperature, right? Those things are what give us climate. And so when you say climate change, something has to change about those two things, right? So either the climate changed in the sense of temperature went up or temperature went down, or climate changed in that precipitation rates went up or precipitation rates went down. It's that simple, okay, guys? So when you think of climate change, I want you now to think about, okay, something has to go up, increase the rate of, or decrease the rate of. So something has to go up or go down, okay? So always establish in that free response question what the change is, okay? So in the Colorado Rockies situation, if the rate of evaporation went up, right, because temperature went up, then that would cause the water downstream to be less because the evaporation rate upstream is too high, or the rate at which the melting ice. So that's the change there would be temperature, that we have an increase in temperature, which is causing the ice to melt too quickly. Okay. And so it's really big that you can establish what the change is. Okay. And then once you establish what your change is, then you just have to connect it to, you know, whether it's evaporation, precipitation, or, you know, what exactly it is you're trying to go with there. Okay. I hope that helped. I don't know. I started bumbling there for a minute. Hopefully you guys are getting it. So this is a good image here of your water cycle. Okay. Again, the connection here, transpiration from plants. Okay. And that's something I think sometimes students have a hard time understanding, is that plants can release water once they get too hot. The evaporation here from the ocean. And a little side fact there, you know, water molecule in the atmosphere will spend about 8 days floating around in the air until it finds some sort of condensation nuclei, whether it be dirt or dust or smoke or whatever, and it forms this cloud, and then we get precipitation from that. Okay. Over here, our precipitation, of course, there's various forms of precipitation. We mentioned earlier, as before we started here, it snowed today. And so there's a little form of precipitation we haven't seen in a little while. And then we see ways in which surface water can be stored. We have a lake here, we have surface runoff. So there's our connection here a little bit. We eventually get to infiltration. And then there's a connection here. It's not in this particular picture, but what is another way, maybe say an underground storage of water? What would we call that? You can type that in the chat if you want to, real quick. Um, so not groundwater, but what's another way in which we store water underground? What is that term called? It's not in this illustration here. So you guys got a word, a term that's not in the illustration that will tell us what we call water that's stored underground here, where my cursor is. Good, we got aquifer. Good, okay. And so now we've connected our water cycle to a term like aquifer, right? And so hopefully when you think aquifer, now you're looking at a connection to either agriculture or drinking water. I live here in central Kentucky, and I used to teach at Scott County High School. And Scott County High School has an aquifer. That's what supplies their community with drinking water. And it's called Royal Springs Aquifer. And so that little spring is actually in the middle of town, which is kind of crazy. So many people drive by it and they have no idea that there's a giant hole in the ground with water in it that goes, it's a huge cavern, but it comes to the surface there. And that's their drinking water supply. And so now you can connect, if I'm looking at free response questions, I'm able to connect the water cycle to drinking water, to agriculture. I'm sure you all have talked about, or maybe if you've heard of the Ogallala Aquifer, which is in the Midwest, basically making up the underground part of Nebraska. And, that's a huge, huge agricultural irrigation water supply. Okay. So our surface runoff, and anytime I hear surface runoff, it automatically takes me to some sort of concept that could potentially lead to eutrophication. It could lead to water pollution. It could lead to the idea of soil erosion. So surface runoff, which is a part of the water cycle, connects me to a lot of other topics that I need to know about. Okay. All right. Again, talking about climate change and connecting here, you increase the temperature, and you're going to increase the rate of evaporation, okay, which is going to decrease the amount of surface water that you might have, right? Again, connecting here, high temperatures, high winds, greater exposure. These are all ways in which we can increase the rate of evaporation. Obviously, if these things go down, you would decrease the rate of evaporation. Be careful on the free response, going back and forth. Like some students will say an answer, this increases this, and then their next answer is, but it decreases this. And so you want to try and be really assertive in your answers. Don't go back and forth or play opposites. Evapro, so transpiration, I think we're good there. We're going to keep moving. Groundwater. Groundwater, the term groundwater, there's a lot of things that kind of come to mind there, right? For me, the connection with groundwater and other areas or other units of topic, when we use groundwater for either drinking or irrigation, that groundwater is sometimes, if you're along the coastline, that groundwater is replaced with salt water. And so we get into this whole concept of what's called saltwater intrusion, right? And so groundwater along the coastlines, when used or overused, can lead to the saltwater replacing it, and that causing what we call saltwater intrusion. And of course, saltwater has a huge negative impact on freshwater plants and freshwater soil, it's going to have a huge impact on those areas. Additionally, if you overpump groundwater, you're going to lead to sinkholes, right? And sinkholes can have a huge impact. The state of Kentucky, we're full of areas of our soil is with limestone, and limestone seems to dissolve very easily to infiltration or percolation or movement of water in the ground. And as that limestone dissolves, it leaves behind it a big giant hole in the ground, a big subsidence. So there's a connection to, say, the water cycle and land use. Okay. All right. The phosphorus cycle. So if you have any questions, anybody have any questions about the water cycle? I've talked quite a bit. If you have a question, you want me to say I didn't explain something very well, or you'd like for me to go over that again, you can just put that in the chat, and Miss Wheeler will let me know that someone's asking me a question, okay? And again, you guys can unmute yourself there and speak up if you want to. All right, so we're going into the phosphorus cycle. I think this is one of those cycles that students forget, right? They forget ideas like ATP, that P stands for phosphate, ADP, we got a phosphate, okay? And so all of these things have phosphorus in them. Our DNA, if you want to jump in there for bonus points there in the chat room, where is the old phosphorus in our DNA? Let's see who's got that little background in biology there. So in the chat, tell me where phosphorus is found in DNA. Or if you want another little bonus question here, we've got the animal cell, and phosphorus has a big part of the cell membrane, okay? And there's a nice fancy term in biology that describes this cell membrane, and you're going to get phosphorus out of that too, okay? So first off, for this particular cycle is to establish the fact that it is extremely important, okay? Phosphorus is extremely important. It makes up our DNA, RNA, ATP, ADP, makes up the cell membrane, makes up so much of the membranes that make up all of these organelles, okay? That membrane being the phospholipid bilayer, okay? Remember, it's that fatty acid tails with the phosphate head on it, okay? No one in the chat typed up what's in DNA here. The phosphorus is that phosphate backbone, okay? So when you're looking at this double helix here, right, we have a sugar phosphate backbone. That's the gold part of this particular image, with the nitrogen bases here in the middle: adenine, thymine, cytosine, guanine. So this is our sugar phosphate backbone that makes up DNA. All right, unfortunately, phosphorus here is locked away in the earth, in the soil. It's in the rocks here in this picture. It's locked away in organisms in the ocean. It's locked away in structural components that make up the oceans, in the ground. Okay, so a lot of the phosphorus that's needed for living organisms is going to be found attached somewhere. Okay. Unlike other biogeochemical cycles like water and nitrogen and carbon, this one has no atmospheric component. So that's huge. Okay. All right. Because of the fact that phosphorus does not have an atmospheric component, so that means it doesn't have a gas stage, right? There's no stage in which phosphorus is transferring through the atmosphere in part of the cycle. Okay. And that's the problem with phosphorus, is because, it's a necessary element, right, for the basic macromolecules of life, ATP, DNA, and so on. But it's very hard to come by because it's locked away in the earth, or locked away in the in a shell or locked away in an organism even, okay? And so phosphorus then becomes a very much a limiting factor. So in other words, it can limit the size of a population, right? Because it is so wanted, right? So no atmospheric stage. So that makes phosphorus very much the limiting factor. All right, remember that. It also makes phosphorus one of those elements that cycles really slow, okay? So, some phosphorus might be locked away. I'm sure I don't know where the example would be, but I'm sure there's some phosphorus in our planet, in Earth, its crust, that has never been released to the environment ever, okay? Because we just haven't gotten to it, and it hasn't been broken down or eroded away, okay? And so that brings us to like this image here. And so what ends up happening is, in order to get phosphate or phosphorus into our living system, it has to be eroded away. So weathering and erosion, okay? In this case, it's being mined. Phosphorus can be mined and then used as fertilizer, and that fertilizer goes into crops, and those animals eat those crops, and we can either eat those animals or the waste of those animals, and phosphorus finds its way into the living system. Here, phosphorus, once it's dissolved, could be then taken up by marine organisms, could go back into the phosphate rocks here, okay? So as you can see, phosphorus is kind of slow going, all right? There's no, you notice we don't have anything up here in the air. Phosphorus is not flying around being transferred by the wind and put back into the living system. Instead, it's all either, it's a solid piece, a piece of sediment there that has to be taken up and absorbed, either by consumption or by, like the organisms down here, absorbing it, okay? All right, so weathering and erosion, that kind of brings us back to how we can get phosphorus into our system. Phosphorus being dissolved, okay? And then the biggest factor here is kind of go back to limiting factor. Sorry, I put that Google Classroom on there. That's my students. They have to do Google Classroom answers when they go through their notes. But anyway, it's a limiting factor. And, we got the little plan here that says I want phosphorus. And so that can lead to some other issues, right? So as phosphorus is such a limiting factor, right? So that means it could limit the size of a population. When phosphorus becomes available, let's say phosphorus became available in an aquatic ecosystem. So in other words, a farmer is using phosphorus to fertilize their plants because their soil lacks phosphorus, okay? So the farmer uses phosphorus as a fertilizer, and then it rains, and what phosphorus isn't taken up by the plant becomes runoff, okay? And it joins that water, dissolved in water, and leads, that surface runoff and takes it to the aquatic ecosystem. Well, the organisms that are wanting and desiring phosphorus so much, they use it up very, very quickly because, again, it's a limiting factor. So when the opportunity arises, they're going to take it up and absorb it very quickly. And that's what leads to what we later learn as eutrophication. So when there's an overabundance of a limiting factor, such as phosphorus, organisms like algae are going to absorb it so quickly that they're going to overshoot their carrying capacity. And then that leads to these algal blooms. And those algal blooms lead to, once you overshoot carrying capacity, you go back to this whole thing where you die back. And then these aerobic bacteria come into the system and they start breaking down and decomposing the dead algae. And then next thing you know, there's no dissolved oxygen inside your aquatic ecosystem. And so that leads to fish kills, all right? And so that's kind of what or a dead zone even. We have in Mexico at the mouth of the Mississippi River, we have one of the biggest, dead zones that's tied to agricultural use or overuse of fertilizers. Okay. So as I'm talking there and you're listening, I'm hoping you're seeing like, man, this simple cycle knowledge or understanding of how the phosphorus cycles through our ecosystem is connected to so many different components of AP environmental science. Okay. Let's see. Of course, we talked about how phosphorus, I mean, again, these slides are going through telling us how phosphorus can get back into the ecosystem. Okay. I talked here, I've got a little thing of detergent here, and how that there's hopefully, I don't know if you've noticed, but a lot of our detergents now will actually say on their label that they're phosphate free. As a matter of fact, I believe under new legislation, all detergents are supposed to be phosphate free, but I could be wrong on that one. I know Dawn was one of the last major, soap companies to go phosphate free. And the reason they went phosphate free is because, again, that example I just explained to you, where phosphorus finds its way back into the aquatic ecosystem, right? And then the algae bloom, and then they die, and then they end up leading to low dissolved oxygen, which leads to fish kills, and it has a huge negative impact on the aquatic ecosystem. And so phosphates in our detergent work really well in terms of cleaning stuff and connecting or making these little bonds to grease and dirt. And that's why they were used in detergents, especially like dishwashing or soap or anything that you might use in the bathroom. And then that extra phosphate that got washed down into your wastewater then found its way into your aquatic ecosystem, leading to these eutrophication situations. All right, phosphorus. You guys aren't really saying much. Am I talking too much? You guys can comment in the chat. You don't have to talk out loud. It's okay. I feel like I haven't talked to students in such a long time. Maybe I've forgotten how to do it. All right. So we get into the carbon cycle. Again, we got a little lump of coal here. We've got our DNA. We got plastics, okay, for carbon. All right, all living things on Earth are carbon based. So that's what we kind of, lean towards is, that organic. Okay, sometimes I think people misuse the phrase, this is organic, and they give us a different meaning of organic. But in the real sense, if you're a chemistry person, organic is carbon. Okay. And if you guys go into college and you take organic chemistry, you're going to have to memorize over 150 formulas of carbon equations, right? Carbon reactions, alkenes, alkynes, and alkanes, right? Most of my students don't struggle with the carbon cycle, because they know what photosynthesis is. And so we understand photosynthesis as what a plant does to create energy, right? And so the plant takes sunlight energy, they convert it to this chemical compound, glucose, so that they can then break it down for energy purposes down the road. So they're called autotrophs, right? So right now, right off the bat, I'm connecting this carbon cycle, photosynthesis, to what a living organisms, the autotrophs, what they do. So now that kind of ties me into those trophic levels, those energy levels that are tied to our food chain or our energy pyramid, right? So there's another connection there. We know that phosphorus takes in, photosynthesis takes in sunlight, carbon dioxide, and water. And as a waste product here, we get oxygen and glucose. And we know that in cell respiration, right, we take in that oxygen and glucose, and then we spit out our energy molecule of ATP. Again, there's a phosphate there, carbon dioxide and water. And that's what we kind of complete the photosynthesis, cell respiration, those two things combined giving us our carbon cycle. Now, for AP Environmental Science, okay, our big question is the sources. Where is this source coming from? Even in the water, where is that source of water coming from? And if we go back to carbon dioxide, a lot of this carbon dioxide is coming from the cell respiration of living organisms, but some of that carbon dioxide is coming from the incomplete combustion of fossil fuels, right? Coal, oil, natural gas. And those things are what are contributing to a much higher carbon dioxide level. And so, do we have the plants, enough plants photosynthesizing, right, in order to take on such a load of carbon dioxide? And the answer is we don't. We don't have that kind of plant. And so this excess carbon dioxide has to do something. And so in some cases, that carbon dioxide may find its way into the ocean. Okay, in which case there are definitely photosynthetic organisms in the ocean, phytoplankton to be one of them, most abundant ones, and they're going to take in carbon dioxide, but we're still actually producing so much carbon dioxide through the use of fossil fuels that even the plants and the ocean can't even consume it and put it to use like we need them to, okay? And so that's kind of even part of the reason why we even have this class, environmental science, is the overuse and releasing of carbon dioxide via fossil fuels, right? So too much carbon dioxide in the ocean, that leads to things like ocean acidification, and when the pH, and so that ties me back into, I need to understand what pH means. And so the more acidic something is, the lower it is on the pH scale. The more basic something is, the higher it is on the pH scale, 7s being neutral. And so too much carbon dioxide dissolved in the ocean, it leads to that carbonic acid, right? So in other words, all the phytoplankton that are in the ocean, all of the organisms that need, say, carbon in their living ecosystem, their living system, they've used it and there's still too much carbon dioxide, right? And that's when we start getting a pH change. And so now that dissolved oxygen or dissolved carbon dioxide is now converting to carbonic acid. And so that can be really bad news for coral reefs, as that ocean acidification dissolves the shells and the structures, the reef structures, because of the acidity. Too much carbon dioxide. And then let's take, for instance, like right now, when I look outside, I don't see any leaves. And so the carbon dioxide levels in my area right now should be actually at their highest because all the trees out here aren't photosynthesizing. They've kind of taken a nap, but the rate of carbon dioxide is still coming out. People are still driving, we're still burning fossil fuels, right? Questions so far? Anything? All right. So when we talk about the carbon storage, we're using a phrase called carbon sinks, okay? And our carbon sinks are trees, rocks, okay, in the form of, like, say, calcium carbonate. The ocean can store carbon. And so we need that, but we're still, the kicker is we're still actually producing so much carbon dioxide that even the trees storing it, the ocean storing it, rocks storing it, we still have way too much to deal with. And then we know that carbon dioxide is a greenhouse gas. And there's something that we talk about, or I talk about in my class, called the global warming potential, right? So how much of a global warming potential is something? And so with carbon dioxide, it's measured in carbon dioxides. And so we're producing so much carbon dioxide that now we have this scale called the global warming potential. And so that's not a good thing for us. So we got a question there on areas with coniferous trees. Are CO2 levels the same year round since they don't stop photosynthesizing as much? And in those areas, you're going to find that the rate of photosynthesis it's going to change a little bit because of the sunlight factor. Okay. Because those coniferous forests, aren't those quite a bit farther from, say, the equator in terms of direct sunlight? And so what you end up having is a different rate of photosynthesis. So our CO2 levels, they end up, in other words, it kind of levels itself out because they don't get as much direct sunlight to photosynthesize. So that's actually a really interesting question. Very good. So let's talk about that. So when you think of like rate of photosynthesis, that actually kind of ties us a little bit into the primary productivity. And so since you mentioned coniferous trees in the chat room there, we might tie that to like a taiga biome or a boreal forest biome, right? So what biomes actually have the highest primary productivity? So in other words, what biomes have the highest rate of photosynthesis? And the boreal forest actually has a pretty high rate of photosynthesis and primary productivity. And then you cancel that out with cellular respiration to get net productivity. Tropical rainforest, good. That's going to have your highest rate of primary productivity. Now, as far as net productivity, the tropical rainforest is not going to have a lot of net productivity because it has so much cell respiration. All right. So in terms of carbon storage or carbon sinks, we're looking at, again, trees, oceans, and earth, rocks, okay? Now, we actually have come up with some other ways that we're trying to figure out how much we can sequester carbon, okay? So carbon sequestering is actually a real thing. It's a real phrase. And we've actually thought about ideas of storing carbon dioxide in the ground. A good friend of mine works for the University of Kentucky, and they've actually talked about taking sequestering carbon and putting it into a solid form, like a carbon cake, looks like a little puck of carbon, and then burning it again. So collecting this carbon dioxide, compressing it into a solid form again, and then reburning it for energy purposes. And so that's going to be, I'd say in the next several years, you're going to find alternative ways to combat carbon dioxide emissions. And that leads us to, things like Kyoto Protocol, some legislation, Clean Air Acts, and stuff like that. You're going to see more legislation that's going to have to address the carbon dioxide emission, as it is a greenhouse gas for companies that are burning and emitting carbon dioxide in the atmosphere. All right. Looking at this slide, I think we're good. All right. Now we're going to tap into the nitrogen cycle. This is the last cycle I'm going to talk about today. We've got a good old molecule here of DNA, double helix. Okay. Really important to note that the majority of nitrogen is found in the atmosphere, where the other cycles like the water cycle and the carbon cycle, we found that the water, hydrogen, oxygen, and carbon, we found that those things cycled very quickly, right? As I'm talking, I'm exhaling carbon dioxide, right? So, we found that they cycle very quickly. Where the nitrogen cycle, this one's going to be a little bit slower because the majority of nitrogen is found in the atmosphere, and our bodies are not adapt to using N2 in any way, shape, or form. Neither are plants, right? And so that slows down the cycle quite a bit. And of course, we already mentioned the phosphorus cycle being super slow because it has no gas state at all, okay? All right, so then we find nitrogen to be a limiting factor, just like phosphorus. And again, go back to the fact that the cycles are super slow. All right. Here's a good old nitrogen cycle picture. Okay. And we're going to kind of break this down here. You don't necessarily have to be able to do much with this, but be able to break it down. Okay. And so we break it down here into fixed NAD. Okay. And this breaks down to fixation. That's the fixed part. So fixing nitrogen into a usable form. Nitrification. Okay. This is taking nitrogen and putting it into a usable form. Ammonification. This is taking nitrogen and putting it into a usable form, right? So these first three phases of the nitrogen cycle are just taking it and trying to put it into a form from which plants can take it up or, you know, well, mostly plants can take it up and then I eat the plant. This last A here is assimilation. This is where the nitrogen is assimilated into the living tissue of the plant. And then finally, we got to make this a cycle. You have to have denitrification. And this is the phase of the nitrogen cycle where it cycles back and could be fixated, nitrified, ammonified, and assimilated. Okay. Remember, it's got to be a cycle. And the D here completes our cycle. Okay. All right. So in fixation, you could have abiotic fixation. You could have lightning strikes. Okay. Or you could actually have nitric acid precipitation. All right. And that would be like NO or NO2 as it's exhausted from the tailpipes of an automobile and it gets dissolved in a cloud and precipitates out as acidic rain. There's one way. So those are all abiotic. Okay. A lot of times people kind of lean towards this, you know, naturally occurring lightning strikes as a way to abiotic fixate into. Now, when I say fixation, we're fixing into gas into a usable form. Okay. And so the next one is nitrogen fixation. Bacteria in the soil or root nodules of plants like legumes, they have the ability to take into gas and convert it to ammonia. Okay. And that's huge. That's really important. So like in my area, we're very rural. So there's a lot of farming. And so let's say a farmer takes corn and then replaces that corn with soybean. Soybean falls into the legume family and they have a little symbiotic relationship with a bacteria called rhizobium. And the rhizobium and the root nodules of the soybean fix nitrogen back to the soil. And so right now in this particular cycle, the nitrogen cycle, I can actually tie into some agricultural practices such as crop rotation, okay, or cover crops. In cover crops, I may plant soybean or Timothy grass or something that has the nitrogen fixing abilities on my land and cover it so it doesn't erode away. So the soil, topsoil doesn't erode away. I'm just trying to fix nitrogen back to my soil so that I can plant corn again. Okay. And if I use soybean, I actually can harvest the soybean and sell it. So I'm not losing money on my land and it's acting and it's putting nitrogen back into my soil. So I'm not having to purchase synthetic nitrogen or man-made fertilizer. Okay. In the process of crop rotation, I'm actually rotating, say, my corn to one field and my soybean to the other. And then every so often I'm flipping those two crops. And the purpose there is that, you know, I'm going to make more money off the corn. So that's why I'm harvesting it, but it devastates the topsoil. It strips it of nitrogen. And so I need to every now and then replace that corn in that field, crop rotate soybean in so that I can get nitrogen back into the soil, right? So we just tied carbon cycle to agricultural practices. All right, in this step here, nitrification, we actually have bacteria that live harmoniously in our soils. You don't really have to know the names of the bacteria, but one bacteria, Nitrosomas, creates nitrates. A nitrobacter creates nitrates, okay? So they take ammonium, all right? So look up here, we've got ammonia in the soil, and they'll convert that into ammonium, NH4, and then they'll convert that into nitrites and nitrates. And I'll show you what those look like on the other slides, okay? Now, these things can then be absorbed by the plant, the roots of the plants, okay? So all of this abiotic fixation, nitrogen fixation, nitrification, and ammonification, all of that is leading to just to get nitrogen in the soil so that plants can take it up through their roots, okay? The last one here, we have decomposers, fungi, bacteria that will break down living organic nitrogen. So they're decomposing, whether it be leaves or dead organisms, they're decomposing them and they're converting that into ammonia, which can be taken up by the root nodules of the plants, okay? Finally here, we've taken up the nitrogen, we've converted it into a usable form, and the plants take it up and incorporate it into their tissues. And then of course we eat the plants, or we ate the animal that ate the plants, and that's how we get our nitrogen. So the nitrogen that's in our DNA is coming from this entire process, okay? Finally, with all of that nitrogen floating around in the soil, not all of it's taken up by plants, okay? Not all of it's taken up by plants. And so we have bacteria, they'll actually, reductase here, they'll actually convert these molecules here back into the N2 nitrogen gas, okay? And so here's our ammonia, our legumes, and ammonium, okay? And then here's our nitrate and our nitrite. I always tell my kids that nitrate, that 3 looks like an 8, right? And nitrite, it's a little bit light, so it's 2. 2 is less than 3. I know you're probably saying what a dork I am, but that's how my kids memorized nitrate, okay? The 3 looks like an 8, nitrate, nitrite, it's a little light, so it's a 2, okay? Now, these are also ions, okay? Now, I haven't spent a lot of time talking about ions, okay? Here's an ion here. Hopefully, you know that ions are charged particles, okay? And that's so unique because what happens, okay, what happens is that this ion, this nitrate, the 3 that looks like an 8, this nitrate it'll bond with water, okay? And man, without getting into too much chemistry, you have to remember that water is this polar covalent molecule, right? And it has this unequal charge on either end. And so what happens is these bacteria, they convert this stuff into these ions. And then when it rains, okay, when it rains, that water will naturally dissolve these ions because of the polarity, the charges, okay? It's because of the charges of the molecules, all right? And that's then how this nitrate and nitrite and ammonium, it's how they piggyback or ride on a water molecule up through the roots of a plant, okay? All right. All right, assimilation. Oops, sorry. We take these molecules here, and they are now assimilated into the structure, the living tissue of the organism. Here I put a limiting factor in ecosystems because it's essential, okay? Nitrogen is absolutely essential to living organisms, and we need it, and that's why it becomes a limiting factor. I put here bacteria converting nitrogen oxides back into nitrogen gas. So denitrification. So we have to complete the cycle, okay? Because I might be talking a little bit fast because I'm running out of time here. But and we have bacteria in the soil, okay, living harmoniously with everything else. And they are converting that extra nitrogen that isn't taken up. So the extra nitrates, the extra nitrites, the extra ammonium, that's not being taken up by the root nodules, they convert it back into gas. However, they don't do this. They just convert because they are chemiotrophs, right? And so they're having to take chemicals in order to get their energy needs met. Okay. And so in some cases, they also produce what I have down here in the corner called a nitrous gas. And this can actually be toxic. It can be flammable. And sometimes it's a byproduct of the man-made conversion or synthetic making of nitrogen fertilizer. And so there's some serious side effects here. So the bacteria, even though they're in our soil and they help complete the cycle of this nitrogen cycle, they can also connect us to a bad part of the cycle. Okay. All right. So I kind of finished up here with this last slide here. May 14th, noon, you should be able to interact with your AP classroom. If you have any questions for me, there's my email address. There are no stupid questions, right? And I am always available. I'm gonna stop sharing and go back to the main page here. And if you have any questions, jump in here with anything at all. Well, I really appreciate your all's time and energy getting up this morning. And I know my kids are all virtual, my students are. And so they don't start interacting with me until, after 12 o'clock. And then they start emailing me and texting me, all hours of the night. I have to put my phone on silent because they're sending me questions at 3 a.m. Hey, that was really good, or that was really bad. But anyway, I appreciate you guys and your time. Debbie, I don't have anything else.
Okay. It is 11:01. Why don't we take a 5-minute break and we'll meet back up here at 11:06. I'm going to go through some FRQs on plate tectonics and soil. I also have a little quizzes to see what you know. So yeah, I'll see you back at 11:06. And as you do that, just a reminder, I have restarted our recording of this presentation. All right, I see them. Convergent, divergent, transform. Excellent. So These three types of boundaries you want to keep straight in your head, be able to tell the difference between each one of these. In divergent boundaries, we've got two plates that are moving away from each other. We see this with seafloor spreading. With convergent, we've got two plates, and there's a couple of different options that can happen. We can have subduction or a mountain building event. And if you know why we might have one over the other, would you throw that in the chat too? So why with convergent boundaries do we sometimes have subduction of one plate under another? And why do we sometimes have a mountain building event? Softer ocean crust subduct. One plate is heavier or denser, might be a better word to use there, but yes, one plate is denser than another. So the oceanic plates tend to subduct over the continental plates because they are denser. Those are made of basalt. Oceanic plates are basalt, while continentals tends to be made of granite-like substance that's a little bit lighter. And so if we have both two continental plates colliding, we'll get a mountain event, or we can have two oceanic plates that collide. Awesome. All right, here's kind of a written out version of what we just talked about: divergent, convergent, and transform boundaries. Transform plates, that's the one I haven't yet mentioned, although you've seen the picture of it. Those are going to move. One is moving in one direction and one is moving the other, and it's sort of a side to side orientation. And then when we have plate movement, we can have faults that result. So the fault right there that you can see in that image is the San Andreas Fault near San Francisco and Los Angeles. And you can actually see that fault line from the air. Anybody know what kind of boundary is at the San Andreas Fault? Feel free to put that in the chat. Yep, transform, well done. And earthquakes are going to occur when we have some lithosphere that ruptures along that fault line. So there's our transform fault. Again, the San Andreas is a great example. What is a good example of a divergent boundary? That's a good example of a divergent boundary or divergent interaction between two plates. Mid-Atlantic Ridge. Thanks, Mr. McCann. Yeah, I've got an image here of Iceland. So Iceland is between the North American plate and the Eurasian plate, and the Mid-Atlantic Ridge forms right there. So it's almost like Mr. McCann and I coordinated his answer there. This is the East African Rift Valley, another great example. You could actually swim. There's some cold water, some glacial water that's filled up this fault in certain areas of Iceland. And you can actually, we snorkeled there when I took a group there a while back. Convergent boundary, probably should have had you guys throw this in chat. Sorry, a little fast with my mouse button. Those are occurring, as we said, where tectonic plates collide. And so you can have two oceanic plates meeting, and that's what forms the Japanese islands. I've got a picture here of the Himalayas. Two continental plates are meeting to form the Himalayas. And then an oceanic and a continental plate meet, and that forms the Andes in South America. So good to have some examples as you're thinking about those. And then if you haven't already kind of looked at where some of these common plate boundaries are found, you don't memorize this map necessarily. I think having some examples like we just talked about is good, knowing what's going on there. But here's an example of an FRQ that might ask you to use some of that knowledge. So similar map as the one I showed you. It says plate tectonic plate theory states that Earth's lithosphere is broken into very slowly moving pieces or plates. Plate movements over vast stretches of time have led to the current orientation of our continents and oceans, and individual events along plate boundaries like earthquakes and volcanic eruptions ensue. Pose periodic threats to human activity and ecosystems. The ring of fire is a term that describes a location of increased seismic and volcanic activity around the margins of the Pacific Ocean basin. And so you can see on this map, each dot represents either an earthquake or a volcano. And maybe you've done an activity in your classroom where you've had to map these out so that you can really internalize the fact that, this ring exists around the Pacific Ocean. So they haven't asked us anything. They're just kind of warming us up, getting us thinking about plate tectonics. Now they're going to ask some questions. So the first one, Japan, Indonesia, and the Philippines are examples of volcanic island chains that have formed along subduction zones between plates in the Western Pacific. Describe what happens when two tectonic plates collide along a subduction zone. So go ahead and answer I, if you would. Describe what happens when two tectonic plates collide along a subduction zone. I'm sure you're typing right now. I'm patient. Using my wait time. And the answer for I is simpler than you might think. You can form an island arc. Awesome. A mountain range. So when two plates collide, that's definitely an option. Would that happen along a subduction zone? And if you also want to respond to II, how subduction leads to volcanic activity, I'm going to share some options with you for both those answers in just a minute. Okay, I'm going to go ahead and go on to the next slide. The simplest answer, is oftentimes, see a nice long one. When two tectonic plates collide along a subduction zone, there can be earthquakes and tsunamis that occur from the movement as the upper pelvic of crust forces kinetic energy to create tremors and potential wave. Thanks, Zoe. That's a good explanation of many events that can happen, like the tsunami edition. Tsunamis was definitely part of this this FRQ. To earn points for part AI, you just need to explain one plate is pushed beneath the other. Or you could have said a trench may be formed at the subduction zone. So fairly straightforward question. For II, in order to earn points, to explain, how that leads to volcanic activity. So Zoe, it's definitely true that we can have earthquakes and tsunamis, that result as a part of that as well. To specify volcanic activity, we just need to explain that as that plate is being pushed down, it's melted, and that molten material or magma is going to rise up to the surface along that subduction zone. And that's what's going to be responsible for the volcanic activity. Any questions about that? And feel free to talk on your mic if that's more comfortable rather than the chat window. Okay, let's look at another component of this FRQ. Although the landscape following a volcanic eruption may appear unable to support ecological communities, over time the area can be transformed through succession. So even though this FRQ did focus on plate tectonics, now they're thinking about, what else can occur because of changes in the community there, the biological community. So I is what is primary succession? And II, how does it lead to soil formation in a volcanic landscape? So take a minute to ponder that and post an answer in the chat. Good. So yeah, there is no soil already there. Excellent. So primary succession is going to be ecological succession that begins in an area without soil, which makes sense because we've had a volcanic eruption. So we're going to be starting with rock. Very good. How is that going to lead to soil formation? Good. Thank you, Mr. McCann. Ecosystem undergoes to form fertile soil again, and so it's beginning without soil. Primary succession is beginning to colonize an area with no soil, and that's what the College Board is looking for. Do you understand the difference between primary succession and secondary succession? And so we've already established in our chat, primary starts without soil, secondary starts with soil. Okay, any ideas about how soil is going to be formed when we've just got rock to begin with? And you might think about what's going to grow on the rock and how that organism is going to help facilitate formation of soil. That'd be a good way to begin. Nice, Zoe, yes. So let's start breaking down that rock. So it might be some sort of physical or chemical weathering. Is there an organism that can help that happen? Primary succession begins with breaking down. Ooh, I saw lichens. Nice, Daya. We're going to break down the parent material with pioneer species like lichens. Excellent. That's what they're looking for. So our first point, again, we're establishing organisms where bare rock, exists. We want to specify that it's without soil. So we earn a point simply for clarifying that. And then for II, we get a point for correctly explaining that organisms are going to physically or chemically weather the rock. And so physical weathering might be, we've got some roots that are going to start to break up the rock. That could be a good way to explain that. But lichens, a relationship between an alga and a fungus, and the fungus is going to secrete enzymes that are going to start to break down the rock, and that's really the best way we can get soil formation happening. And then decomposition as more organisms begin. Okay, any questions about that part of the FRQ? All right, let's see what else they'd like to ask us. In addition to volcanic activity, highly destructive tsunamis are generated along Pacific Plate subduction zones. So CI says, explain how a tsunami is generated along a subduction zone. And CII is describe one negative ecological impact that they have on coastal environments. And so Zoe had mentioned that tsunamis are going to occur, which is excellent. We just want to be specific about how it's generated. And if you haven't really thought about the how, I might be a little bit hard, but it's a relatively simple explanation that I hope you'll remember after our discussion today. You might think about negative ecological impacts they can have, and those can be pretty straightforward. So addressed either or both of those in the chat, and then we'll look at what College Board was accepting. Potential energy is released when the plates collide with each other. Good. Subduction causes kinetic energy release and then forces up some of the water. I like this vocabulary that causes those waves that then get propelled to shore. Good. All right, I've got two options for CI. Feel free to address that question, or I'd love to see at least one that addresses the second part. What's a negative ecological impact that tsunamis have? destroy property. And if we can focus on ecological, that's good. That's absolutely true. They destroy property. What else might they destroy? Habitats, right? So we want to make sure that if it says ecological, that we focus on that, because it's easy to think about. I always think about human impacts too, you know, and so it's easy to focus on that. But we want to make sure we deal with whatever question they're asking, and this one is ecological. So rapid water displacement is kind of the phrase to remember when you're thinking about how tsunamis form, because you have this movement of land that's going to be, you know, dropping or rising up, and that rapid water displacement is what starts the tsunami. So we get this underwater earthquake. That was part of it. I think you guys are pretty comfortable explaining that part. And then to earn that second part, you want to talk about rapid water displacement. Okay, just to clarify too, I'm showing you the scoring guides to kind of clue the readers into what they're looking for, but they want you to be able to explain this, and so you wouldn't want to just write rapid water displacement as the only thing. You want to be able to explain how that results in a tsunami. All right, for CII, describe one negative ecological impact that tsunamis have on coastal environments. And so we got destruction of habitat. I think that's awesome. I would just try and be as specific as we can and add an explanation of what's on the coast. So mangrove forests, destruction of mangrove forests, and, you know, the habitat they provide. So thank you, Mr. McCann. Remember, ecological property is anthropocentric. Yeah, so property is about us, exactly. Flooding, nice. I saw Alan added due to flooding. So flooding from the waves can create saltwater intrusion. So this is a nice piece to elevate your response. The water coming in is salty, and it's coming into coastal regions that may not have that high of a salt concentration. And so that's going to, you know, impact those species, because many of them have a range of tolerance for salinity, and it might be higher than their range of tolerance. And then really you only need one of these, and you could have said drowning of terrestrial species. So fairly straightforward. Any questions about how you earn points for that section of the FRQ? All right. Part D says Southern California experiences periodic devastating earthquakes along the San Andreas Fault, a transform boundary located along the eastern edge of the Pacific Plate. Describe what happens to the tectonic plates along a transform boundary at the moment when an earthquake occurs. That's our I. Describe what happens to the tectonic plates along a transform boundary at the moment when an earthquake occurs. So if you'll throw some information in the chat, guesses are always welcome and appreciated. All the built up pressure released, nice. Anyone want to add to that? Score and slipping as the pressure release causes them to catch on one another. Nice. Good vocabulary. Okay. If you want to go ahead and add any more for DI, please feel free, but let's also see some responses for the second part, DII. Describe what happens to the tectonic plates along a transform boundary during the time between earthquakes. During the time between earthquakes. Based on the good answers we've already got, I'm thinking you all know what's happening in between earthquakes. Tension is building between the tectonic plates. Nice, 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 nice. Okay, so College Board, I see another pressure buildup. Yes, nice. Um, so for DI, a large amount of energy is released, and being able to explain that earns a point. And you might also say the plates suddenly or rapidly slide past each other in opposite directions. And I think Zoe was starting to formulate an answer that would have included that. Just that sudden slide past one another. If we were in my classroom, I'd put pressure down in my hand and then eventually kind of let it slide forward, and it's going to jerk forward, and that's a good representation of what's happening when an earthquake occurs. In between earthquakes, you guys nailed that one on the head. Along that transform boundary, we have the faults that are binding or locking up, and so we have this buildup of pressure. In between earthquakes, we have this buildup of pressure, and then when the earthquake occurs, we get that release. So nicely done. I think you guys would have done pretty well in this FRQ. Okay, I'm going to switch gears just a little bit and see what you know about soil, and we'll see how smooth I can make this transition. I am going to stop my share for just a minute. Actually, I'm using 2 laptops. Maybe I don't need to do that. I'm going to put a link to a quizzes on soil. Thank you for your patience while I pull up this link. And I want you guys to you go to joinmyquiz.com, and I'll put that link in there too. And then I'm going to give you the code to enter. So there's the link. Now I'm going to give you the code that you need to enter in order to join this quiz. Here's the code link. Thank you, Leslie. I can do that too. All right. So I got help from a friend, and she said just share the link and you should be able to directly click on that. Ooh, I hear some people coming in. Nice. And I'm going to stop sharing, and I'm going to put our top 5 folks in so you can get credit for being awesome. I've got 1 person in. Love to see a few more. Love to see a few more people in before I start. Sorry, I know sometimes it is slow when you first go in. Yes, folks are popping in. Excellent. All right, I got 6 participants in there. Give you another moment to join. And sorry for those of you that are having trouble loading. Hopefully I can start the quiz, and you might find that it lets you join even after I've started, so no worries. Thanks, Tina. So that it might be faster that way then. I'm not sure which way will work faster. I've got 9 folks in. That's almost half of us. Seems sort of like critical mass, so I'm going to go ahead and start it. Good. We've got 10 people in. I see some more folks are joining. Excellent. Got some nice streaks going. It's a shame we're not all in class together so you could trash talk a little bit. Realize my recording's been paused for a while. Nutrients are often dissolved in water. And so if we don't have the ability to hold water, we also don't have the ability to hold nutrients. And finally, sand has good aeration. Air can penetrate very well. So clay is really the opposite. And I think it's helpful to remember those two, focusing on sand and clay, and remember silt's just in the middle for all of that. It's hard to get, it's hard for water to get into clay. Doesn't penetrate through it very well. Clay is very good at holding water and nutrients, maybe so good that plant roots don't have access to it. So that's not always a good thing. And it's not very aerated. So if I wanted to build a pond, what kind of soil should I use? If I want to build a pond, what kind of soil would be best to do that in? Yeah, clay, not sand, right? That's not going to be a pond for very long if I use sand. So that's a pretty basic question, but kind of what you want to be thinking about as you're reviewing soil. You should know a bit about soil tests and what information they give you. So we've talked about texture. I showed you some images of texture. We just talked about how texture can tell you about water holding capacity and porosity, but you can actually do physical tests where you dig a hole, you add water, and you look at how well it's held there. Bulk density, that's also a test I often do in the classroom, where we look at how compacted the soil is. That gives us a information about pore space. Does anybody know what color of soil can tell you? Like if I'm buying a farm and I dig into the soil and, if I want to grow crops there, what color do I want that soil to be? Dark, rich brown. Nice. Yeah. And that tells me there's lots of nutrients. So soil color, it's a physical trait, but it can tell us about nutrient content. The lighter colored soil we associate with sand, and sand we know does not hold nutrients or organic material very well, and so it's not good for growing plants. Color can also tell you if an area floods. Gray soil where the iron in the soil has been reduced tells you that area has flooded recently. And that's kind of good if you're going to be a property owner and you want to know that it might have floodplain or not. And then the chemical tests, pH, how acidic or basic is the soil? Why would pH be important for you? And you can think about, I bought a farm and I'm going to have the pH tested by the Soil Conservation Service. Why would that be important? If it's too acidic, plants will good. If it's too acidic, plants will have difficulty growing. Thanks, Daya. Yes. And it's really going to determine what plants can grow there. Some plants can tolerate a little more acidic soil and some do not. Excellent. Yeah. Range of growth. Awesome. So the elements N, P, K, and S. So, my nitrogen, my phosphorus, my potassium, my sulfur content, that's going to tell me how much maybe, organic material or inorganic fertilizer that I'm going to need to add in order to farm an area. Salt content is important, and metals can be toxic to plants, and so that's going to be important information too for me to know. Okay, I'm going to go through a couple more ideas quickly. I know we're getting close to our 12 p.m. stop time. So make sure you understand the difference between weathering and erosion. So weathering is when I break down the rock into soil particles, and erosion is when those soil particles move. So erosion can occur when we have that soil or organic material moved by water or wind. And it's more likely to occur when soil is bare or exposed. Okay. Can you name an agricultural practice that will help me avoid bare or exposed soil? Excellent. Yep. Cover crop. So maintaining crops, doing some kind of crop rotation where I'm always, I've always got something on the soil. That's gonna reduce my erosion because the soil nutrients are valuable. So as a farmer, I'm going to want to maintain those. And I also think about if the soil is removed by water or wind, where is it likely to end up? And you might think about what problems it's likely to cause there.
Wasn't that the problem with the Dust Bowl? Because it displaced so much off the middle of the U.S.
Absolutely, yeah. And so that caused a major problem because those are areas where we grow food. That's our that's the breadbasket of the United States. And Daya added that soil is going to end up, those soil particles are going to end up in bodies of water, right? And they can go back to what Mr. McCann was referring to earlier, eutrophication. So knowing how to maintain our soil, I'm throwing these agricultural practices up without much explanation, but I want you to know that having some of those in your tool belt so that when you're asked on an FRQ, how can I maintain soil quality? Those are kind of what we're looking for, what the College Board is looking for. Okay, well, that was a whirlwind tour through biogeochemical cycles and Earth's resources. We definitely could have talked to more. We could have gone over some more FRQs, but I hope you found today's presentation valuable. I want to show you where to get a copy of this recording, and I recorded almost all of it. I did realize towards the end that I was missing part of it, but the content review sessions are all going to be at bit.ly /ADVKY. So those little bit.ly HTMLs, hopefully you've seen before. Pretty easy way to get that. And there's some more information about how to get in touch with Advanced Kentucky or our Senior Content Director for Science, Lua Campara. Mr. McCann and I were really grateful to have you this morning, and hopefully you'll be at our next content review session on February 13th. You're welcome. I hope it was helpful.